let's take a look at quantum physics and wave-particle duality. And to do that, we're going to look at three different experiments. We're going to look at the photoelectric effect, at the Davisson-Germer experiment, and Compton scattering. So let's start with the photoelectric effect. The idea here is that we have a metal plate, and we shine light on the metal plate. And then we observe whether or not electrons are kicked out of the metal, and if they are, how much kinetic energy they have when they're kicked out. So the idea behind this is that if here is the metal, inside the metal there are these free electrons, right? Because a metal is a conductor, so there's free electrons floating around. If we shine light on the metal, light, like all traveling waves, transmits energy. So the incoming light waves would transmit energy to the electrons. If an electron gets enough energy from the light waves, it can get enough energy to be kicked out to escape from the metal. And it was known that an electron required a certain amount of energy to escape from the material. And the minimum amount of energy that's required to escape from a material is called the work function. It's represented with the Greek letter capital Phi. Don't get it confused with flux. And the work function for most materials is on the order of a few electron volts. So they perform the experiment, and they have unexpected results. This is a summary of them. Let's imagine that they try different frequencies. So I'll organize the frequencies along left to right, and then they try different intensities, and I'll organize the intensities up and down. So first, let's think about what happens if you have a low frequency and a low intensity. They try that, they send in low intensity, low frequency light, no electrons are ejected. So they increase the intensity, and they think that, okay, well, more intensity means more energy is being sent in, and maybe electrons will be ejected. However, no electrons are ejected. So they increase the intensity even further. And even with a huge amount of intensity, sending in a huge amount of energy, no electrons are ejected at this low frequency. So they go to a higher frequency, and they try it again. Low intensity, but a higher frequency. And in this case, a few electrons are ejected with very low kinetic energies. So they increase the intensity of this higher frequency light, and what they find is they get even more of these low kinetic energy electrons ejected. And they increase the intensity again, and now they find they get many, many low energy electrons ejected from the metal. So then they go to a higher frequency with a low intensity. And what they notice is they get a very few electrons ejected, but they have high energy, high kinetic energy. So they increase the intensity, and now they get more of these higher energy electrons ejected, and then they increase the intensity again, and they get even more of these higher energy electrons ejected. So the pattern that they notice is that the frequency is what determines whether or not an electron is ejected from the metal. It's not the intensity which determines whether or not an electron is ejected. It's the frequency. The intensity, instead, affects the number of electrons which are ejected. It doesn't change the energy of the electrons which are being ejected. It just affects the number of those electrons which are ejected. So the explanation for this behavior is from Einstein. Einstein suggests that light, instead of treating it as a wave, we treat it as coming in quanta. Quanta, and that's where quantum physics comes from, by the way, but quanta are little packets. And when we talk about light, these little packets, these quanta, are called photons. So if we think about light not as a wave, but instead as made up of little particles called photons, and if each photon has an energy equal to h times f, where h is Planck's constant, then it starts to make sense. Because if we send in this low frequency light, then that means that all of the photons that we're sending in have low energy. And so each little photon that comes in doesn't have enough energy to eject an electron. But if we increase the frequency, then each photon carries more energy. It's a packet that contains more energy. And so then each photon is capable of ejecting an electron from the metal. However, when the electron is ejected, it doesn't carry much kinetic energy because that photon that brought energy to the electron didn't bring a lot. It just brought enough to kick the electron out and maybe have a little bit of extra kinetic energy. But if we send in light with a higher frequency, then we have photons, and each photon carries a larger amount of energy. And so when that large energy photon comes in, it has enough energy to kick out an electron, and the electron has an additional kinetic energy when it leaves, so we get a high energy electron ejected from the metal. So if we go back to our little grid here, along this axis we have frequency, but that's also an axis that shows us the amount of energy carried per photon. And then along this axis we have intensity. But intensity is also standing in for the number of photons that are being sent in. So over here, if we have low frequency, then we have a low amount of energy per photon, so we send in very few photons with low energy. They don't have enough energy to kick out any electrons. We send in a higher intensity, that just means more of these low energy photons, and these low energy photons, none of them have enough energy to kick out an electron, so no electrons are ejected. And even if we send in a huge number of these low energy photons, no electrons are ejected. None of the photons are able to eject the electrons because the photons themselves do not have enough energy to do so. At a higher frequency, the photons are able to kick out the electrons, but when the electrons escape, they only have a small amount of extra kinetic energy. And if we send in more of these photons by increasing the intensity, we get more of these low energy electrons ejected. And if we increase the intensity even more, we get even more of these low energy electrons ejected. And then if we increase the frequency even more, we're increasing the energy per photon. And so these photons carry large amounts of energy. And even if we send in a few number of them, each one has enough energy to kick out an electron with a large amount of energy. And if we increase the intensity, we just get more of these high energy electrons ejected. And if we increase the intensity even more, we get even more of these high energy electrons ejected from the metal. Now we can write an expression for the energies involved here. The energy of the incoming photon has to equal the kinetic energy of the ejected electron plus the work function. Because remember, the work function is the amount of energy that's necessary to kick the electron out of the material. So the incoming energy is equal to the outgoing energy of the electron plus the energy that's lost just getting the electron out of the material. And we can replace the energy of the photon with h times f, and we can rearrange it a little bit. So the energy of the ejected electron is equal to hf minus the work function. Now the energy of the ejected electron that's actually the maximum possible energy of the electron when it leaves. The reason why this is the maximum possible energy of an ejected electron is because it actually can require more energy to eject an electron from the material. The work function just tells you the minimum amount of energy that's necessary to kick an electron out. So here we get this expression. The maximum kinetic energy of an ejected electron is equal to hf minus the work function. And this is confirmed by observations. In fact, there's a pretty famous graph that's related to this. If we graph the maximum energy of the ejected electrons versus the frequency of the incoming light, this is the graph that we find. So below a certain frequency, I'll write f0, and this is called the threshold frequency. Below that threshold frequency, no electrons are kicked out. Above that frequency, the maximum energy of the ejected electrons goes like this. Now, if you compare this to the expression we have right here, you can see this line right there has a slope of Planck's constant, and if we were to extend it down, it would have a y-intercept equal to the work function. So the outcome of the photoelectric effect is that we can predict and explain the observations of the photoelectric effect if we treat light as behaving like a particle. Now that's a little bit problematic because in other ways, light definitely behaves like a wave. Light diffracts, it refracts, it reflects. It has all those behaviors that we associate with a wave. But now we're seeing that observations of light can only be explained if we treat it like a particle. So let's move on to the Davisson-Germer experiment. In this experiment, a beam of electrons is incident upon a nickel crystal. It's not really important that it's a nickel crystal, but what is important is that the nickel atoms in the crystal are equally spaced. So after the electrons pass through this crystal, there's a screen, and wherever the electrons are incident upon the screen, you see a bright light. Okay. So notice that these separations between the atoms, there's these little gaps between the atoms, and they act like slits. So if we have a whole bunch of these slits, it's acting like a diffraction grating. But the electrons, what we'd expect is electrons, we imagine them like little bullets, right? And they would pass through the gaps and hit the screen in one place. However, when this is done in a laboratory, what's observed is we don't get a single dot, like little bullets passing through a lattice and hitting one part of the screen. Instead, the pattern that's observed on the screen is more complicated. The electrons hit the screen in a diffraction pattern. The electrons, when passing through these slits, diffract. The electrons exhibit wave behavior. And that's very strange, because up until now we've been thinking about electrons as particles. But now in the Davisson-Germer experiment, the electrons are behaving as though they are diffracting. And it turns out that when they diffract, they behave as though they are waves with a wavelength equal to Planck's constant over the momentum of the electron. This wavelength here is called the de Broglie wavelength. The de Broglie wavelength gives us the wavelength that's associated with the wave-like nature of matter when that matter has a momentum p. So after we see the photoelectric effect and the Davisson-Germer experiment, we ask ourselves, is light a wave or a particle? Is an electron a particle or a wave? And the answer is, light is light, and an electron is an electron. In some ways, light behaves like our concept of a wave, and in other ways, light behaves like our concept of a particle. And likewise with an electron. An electron is an electron. In some ways, an electron behaves like our concept of a particle, but in other ways, an electron behaves like our concept of a wave. This is the idea behind wave-particle duality. On a very, very small scale, matter and energy can be described using the wave model and the particle model at different times and in different situations. The concept of the wave and the concept of the particle are abstract ideas that are created by scientists to describe phenomena. Neither light nor electrons or any other matter has to be one or the other. It doesn't have to pick a side to be a wave or a particle. In some circumstances, electrons behave in wave-like ways, and in other circumstances they behave in particle-like ways. And same for light. That's the idea behind wave-particle duality. Last of all, let's look at Compton scattering. So in Compton scattering, we have very high frequency light, usually X-rays, incident upon an electron. Now, what we might expect is that if we have incoming light, it might diffract around the electron, or perhaps the electron will absorb some of the energy from the light and gain some kinetic energy. What's observed, however, is that the electron is sent off with a certain amount of kinetic energy in a certain direction, and the light changes direction and also changes its wavelength. So the way that this is explained is by considering the light to be made up of photons. So imagine one photon incident upon an electron. The photon comes in and interacts with the electron. And after that interaction, the electron moves off in a certain direction with a certain kinetic energy, and another photon moves off here. Now, the incoming photon contributed some of its energy to the electron. So the photon that comes out of the interaction has less energy, because again, some of that energy was transferred to the electron. So that makes some sense, because energy is conserved in this interaction. What's strange, however, is that momentum is also conserved in this interaction. So the incoming photon carries some momentum, and after the interaction, the momentum of the system is still the same. Now that's weird, because a photon, how can it have momentum? A photon does not have mass, so what is its momentum? Usually we calculate momentum as m times v. Well, what's the momentum of something with no mass? It turns out that you can calculate the momentum of the photon using de Broglie's wavelength. De Broglie wavelength is equal to h over momentum. So if I flip this around, the momentum is equal to h over the wavelength. The momentum of the photon is equal to Planck's constant over the wavelength of the photon. So Compton scattering is another example of light displaying or exhibiting the behavior of particles. And if we were to apply energy conservation and momentum conservation, we could derive the following relationship. I'm just going to give it to you without the derivation. Lambda f minus lambda I, which is the change in lambda, is equal to h over me times c times 1 minus cosine of theta. So to explain this, I'm going to redraw the idea behind Compton scattering. We're going to have the incoming photon here, and the incoming photon has a wavelength lambda I. After the interaction, we have the electron moving out over here, and we have the photon moving off over here, and the photon is going to move off at this angle theta. Theta is the angle between the initial direction of the photon and the outgoing direction of the photon. And the outgoing photon has a wavelength lambda f. So that defines lambda f, lambda I, and theta in this equation. The only other thing to define is me right here, which is the mass of an electron.